So hi, everyone. My name is Subash Kannoth, and thanks for introducing me, Daniel. And I'm a colleague of Daniel and working for Fraunhofer ISE Germany. And yeah, my main focus is on Industry 4.0 and interoperability between communication protocols. And with this paper, I am going to explain about interoperability of OPC UA with other protocols in the other IoT protocols in Industry 4.0, and how that can be achieved with an architecture, an architecture proposed by our department, our Fraunhofer ISE, which is called Virtual Automation Bus Architecture. So just before, some of the concepts are already explained by Daniel here about Industry 4.0. In the current scenario or current world, or called Industry 3.0 era, we have something called as traditional automation pyramid, which actually which is shown in this picture here, which is in a layered architecture, with each layer responsible for different responsibilities in the plant. So the field devices are more into the sensors and actuators, which is being controlled by the PLCs for reading and writing data and actuating the actuators. And above that, we have SCADA, which is a uniform distributed system which controls the PLCs. And the MES systems, or manufacturing execution systems, are other one which actually orchestrates the SCADA or orchestrates the production system. And at the upper layer, we have the ERP system management or management system, where the management look into the systems, they have the access. So here, one of the main problem with Industry 4.0 is, or one of the main aspect of Industry 4.0 is achieving changeable production, or achieving more flexible production with less effort. So in order to do that, with this traditional architecture, it is not easy, because the traditional architecture actually have very strong coupling between each layers. So, so for example, if you want to change a production schedule, you want to have changes in PLC programs. Normally, PLC programs are cyclic programs, which are once programmed, and it is also difficult to change these programs in terms of effort. So, in order to achieve changeability, we have a restriction here. So, Industry 4.0 actually proposes another architecture, or which Daniel already explained before, which is peer-to-peer architecture or device-to-device communication. So device-to-device communication enables this changeability to a bigger extent, because in this context, each layer have flexible capability of communicating with other layers, mainly using techniques such as service-oriented architecture. So, so in order to do this peer-to-peer communication, you need to understand. Every layer should understand each other. Yeah, this is a big problem. Each layer will have different communication protocols. Yeah, different way of communicating, and each layer should understand each other. This is a big problem when we migrate the plant to Industry 4.0, and various protocols have to understand each other. This is something we address with this work. We mainly consider OPC UA, because OPC UA is one of the important protocols proposed by a standard in Industry 4.0 called RAMI, or Reference Architecture Model for Industry 4.0. And OPC UA is very vast, used in most of the industry for years. So we actually tackled the challenge of how we can interoperate OPC with any other IoT protocols with our virtual automation bus architecture. So, which enables the cross-layer interaction between different layers in automation pyramid. So here, the challenges with interoperability is there is no generic protocol translator exists for OPC UA with other IoT protocols. There exists no work, or you cannot say how we can interoperate with OPC in a very abstract way. So in general, we have to cope up. If you want to translate OPC with any other number of protocols, it is obvious that we have to consider n-1 translations. Translation in the worst case, because you don't have to translate itself. Yeah. So, which is actually expensive when you consider this highly growing industry, because a production process can result changes in everywhere. So how we can tackle or we can achieve that with virtual automation bus. So a virtual automation bus architecture is actually consisting of an information model and a set of primitives. And we call it as intermediate language. Information model is a reflective data structure with elements which has types, and we choose these types based on how much platform independent we can go, and also it has also one. It has 5 primitives, which is borrowed from old database systems. Like you all might be familiar with the CRUD systems: create, read, update, and delete primitives. And we have an extra primitive called Invoke, which is important especially in the case of OPC UA, because OPC UA can have remotely invocable procedures in server. So something like a remote procedure call. So with these primitives, a large extent of protocols can be translated. So we prove that with this work, we prove an interoperability between HTTP and OPC UA. So in general, we can extend to other protocols. So one thing I want to remind here is this virtual automation bus acts as a bridge or a common language between many other communication protocols. So any other source protocol which has to be translated has to implement these virtual automation bus primitives and type system. So that any other protocol can communicate through this language. So the basic type system of virtual automation bus is here, and also the other table 2 shows the primitives which supports and actual semantics of that. What does it mean with these primitives? So we have chosen these types based on the mostly because most of the programming languages support all these types, and base types like Boolean, integer, double, and string, and the composite data structures such as map and list. So with this, we can implement or very large extent or express very large extent of capability. And also with the primitives, create actually creates an element VAB with an identifier and the name of that element, and identifier is actually a unique path to that element. You can see VAB as a tree structure with each elements identified with a unique ID, path, and name. And the value is a value of the type. It could be of any of these complex or base types. So here one change is Invoke is which have an ID, name, and arguments. The arguments are arguments which has to be passed to the callable procedures. So just jumping into a very short overview of OPC UA and what it is, and OPC UA, which is very similar to virtual automation bus architecture, which is a client server, which uses a client server models. Also it is not only a protocol but also has an information modeling capabilities. For example, you can model really object-oriented models in OPC UA server, Yeah, so which is very attractive in terms of implementing digital twins, by the way. So there is a reason why OPC UA is considered as one of the most important protocol in Industry 4.0 domain. We can model digital twins, like from the last papers, Daniel has explained it, and you have the layered architecture of OPC UA on the right side, where you have these different mechanisms, client server, and OPC UA also support publish subscribe mechanism, which is not important in this context of this paper. So, and also you can see the blue layer where information modeling capabilities. And OPC UA also supports, provides some base modeling capabilities, which is shown in the yellow, where you can use different objects and instantiate that object. And you are also allowed to extend it, like inherit from that and extend, or they call it as combining specification, which is shown as in green, and also vendor specific changes. So, and yeah, and so these are the different types of nodes possible. Okay, before that, I would like to show this here. And every object in OPC UA world is called nodes. Yeah. So simply in object-oriented programming, you can draw these class diagrams or UML diagrams, which is shown on the left side. So each object instance of that that object is represented as node in OPC UA world. Here you can see, and each node can have relationship with other nodes, and in OPC UA world it is called as references. And each references semantics is actually defined by a type of reference, which it is. For example, in the right side you have these blue diagrams. You can have a parent-child relationship, child-parent relationship, has component relationship. And in the next slide shows some of the base. This slide actually explains what are these type of nodes, and so what are the types of nodes and what these type nodes are capable of. And for us, the most important node is a variable node, which actually can store a data, and object node actually abstracts real-world objects in modeling. So you can have other types of node like object type, where if you want to create custom object type other than OPC UA, you use these object type or variable type nodes and you extend it based on the requirement. And in OPC UA, in order to communicate with an OPC UA or OPC UA server, you actually need to know the identifier of the node. So you have to, a node identifier is a tuple composed of a namespace index, type of identifier, and identifier value. So here you can see every OPC UA node preserves a namespace table which maps namespace of a node to a value, a number, an integer number. So when you create your own specification OPC UA, you probably will have an identifier, a namespace, and your nodes is usually defined in that namespace. That is a good practice which is being followed in OPC UA world. And so whenever you want to, for example, if you want to access a node in this one namespace, you specify that the identifier of the namespace and the name of that namespace. That's why different types of nodes are possible, like numeric string or GUID or byte string, and so on. So how we can create virtual automation, extend virtual automation bus into OPC UA? This is a question. So the right side shows a meta model of VAB counterpart in OPC UA world. So these green boxes here are actually OPC UA standardized, and blue boxes are actually the types we extended for VAB architecture. So we have, as I showed before, that we had different types of types of data types in the VAB. So each types I have to create, we have to define an object type for that. So we have semantics for each type, and also for operation, we have standard operation types. So, and also we have as I told you before, that the relationship between each nodes are expressed using reference type. We have to introduce two reference type, which is shown in the right bottom corner. Has element that has entry, which has entry is which is a reference type which has a meaning that it is an element of a map, and other is has element as has a meaning that it is an element of a list. You can see it is inherited from has ordered component, which is standard reference type. And has ordered component, we use this reference type because in a list in VAB is ordered. It is so you have to have an index, and whenever you add an element to a list, it will always append it to that. So semantics is important here. So here is that how primitives are. The before slide maps the types with different OPC UA types, and here it maps the semantics. So when you create an element in VAB, it has to be properly mapped to the OPC UA service, how a node should be created. So, so when you create an identifier, these ID, name, and value, it has to invoke two procedures in OPC UA server. It has to create a node and assign the value of that node. So initially, the two procedures will be called add nodes and write. And the node ID should be resolved from these three arguments, ID, name, and value. So for that, the other primitives are similar. So I'm not going to explain everything because the arguments are same. So the challenge is to translate that. The aim is to translate this ID, name, value to node ID. So we have to use a standard OPC UA translation procedure called translate node ID to browse path to node ID. So this right side picture shows a UML of a VAB model. It is a simple model with gas tank and sensors and associated values to it, and you can see each object is accessed through a path, a unique path. In OPC UA world, you can see on the right side, it is equivalent to a browse path. And a browse path is, in addition to the names, you have some number in front of it. It is actually the namespace of that node where the node resides in. Usually, in OPC UA, when you create an information model in OPC UA, you should specify where should it start. The object node is a root in OPC UA where you can start the model. And this is always present in OPC UA server. This is why, because it goes to zero namespace, which is shown here in the right corner in the green, which is a standard namespace in OPC UA. And the 2 number is our own namespace where we create our nodes. So this is directly translatable here. The only thing is we have to get back the node ID. For example, for the node gas tank, the node ID is 1000. So you need, if you pass object gas tank, it should get a number 1000 in order to access that or do any changes in that. So element identification is done through actually browse path node ID translation. Yeah, in the last point here, I have shown an example of translating gas tank sensor temperature, so with different with the corresponding browse path. This browse path has to be translated to node ID in order to access it. And yeah, it is straightforward that you can translate it in complexity of 1 time. This is 1-to-1 translatable. Okay, so here as a proof of concept, we showed how to interoperate between OPC UA and HTTP through virtual automation bus architecture. So in order to do that, we had to implement HTTP on the VAB side and OPC UA on VAB side. And HTTP, it is straightforward. We have mapped create to these requests, HTTP primitives, and that corresponding path has to be mapped to the, and in VAB, we already mapped it before in this slide, that we have these primitives in OPC UA. So we have some implemented a gateway architecture, or we propose a great gateway architecture which uses VAB in protocol interoperability. So this is a picture is shown here in my screen, how such VAB gateway works. So when you have industrial application which works in HTTP REST, for example, which if wanted, it comes from an MES system, or it looks for a temperature value from the sensor, and VAB gateway actually translate that to VAB language, and from VAB language it translate to the OPC UA. So you can see HTTP GET is mapped to read to corresponding browse path and corresponding values returned. So in order to evaluate such an architecture, we actually measured the round trip time in two different platforms, and also we measured how much data overhead such a gateway introduces. So this is the part of our evaluation, and we did it for 500 samples each, and took the average of that. And the main evaluation is done for base data types, base variable types, and also for a real-world industrial model, which we took from one of our customer projects, our research projects, which is a glue manufacturing plant, which is shown here, which has different nodes, and the rounded rectangles are actually nodes which store values. So we evaluated our translation capability by retrieving and writing to this model, and also to base types of base data types. So the evaluation is performed in 3 different platforms. One is R&R IoT Gateway, which is very most popular in industry automation now, because this has already embedded system which has the Linux system running on it, and with different interfaces, and also an OPC UA server hosted on it. And one with a personal computer with the Open 6254 OPC UA stack, which is very commonly used in industry now. And also before evaluating, we did an average ping latency between client and server. So in both cases, it is approximately same. And these are some of the results of our RTT's round trip time. So these B, S8, S16 are types which VAB supports, and these are the plots. And you can see that ping one is OPC TCP, is the OPC protocol, and also OPC TCP star is OPC UA protocol without using VAB. So you can see the types are actually almost same. There is no much overhead on base types, which is in terms of other part of the protocol which creates delay. And one thing which is noticeable here is the difference between ping and the orange, because the difference between ping and orange is the node ID translation difference. So in this case, every node ID should be translated from a VAB path, which takes some time. Yeah, this overhead is actually that. And the blue and other graphs are different because of HTTP has more data over when you compare to OPC UA binary protocol. And these are the results of the same thing, which in addition that we did for that model of gas tank. So it also shows a similar pattern. You can see OPC TCP star is considerably smaller here because the node IDs are already known before. And the last plot here is actually a ratio between OPC UA, TCP, and HTTP, and how much HTTP is creating overhead over OPC UA. And you can see it is almost creating like 20% and so and so. So here we also measured another evaluation based on how a number of nodes affects accessing a nodes. So when we have two plots here. When you increase number of nodes, how much time it takes to access the whole nodes, which is shown in blue, and the pink one is when you nest nodes to a depth. For example, to the same depth, how much time will you consume to access that node to a depth? So what our results show, it is almost linear, which is good in terms and is not actually creating. It is actually an expected results as well. And it also, I would say, it also depends with the OPC server implementation. But in our case, both servers almost behaved similarly. I think the PC has some fluctuation because the other one, Arendar IoT Gateway, has some Linux kernel which is very optimized for real-time operations. And we also evaluated the data overhead, how much data created. So here you see HTTP, OPC UA, and also put and get. I mean, we only consider read and write primitives because these are mostly used primitives. Create, delete, and update is very less used. So, so we evaluated for read and write. So you can see here the request OPC UA TCP, the second column here. So here the request and response is greater than the from HTTP. So it is expected to have more. So the thing is, it is greater because OPC UA response has some other data, some other information which is not relevant to VAB, which is neglected here in HTTP. So in a way, it is also good for in VAB because it has less data to process. So it also shows that there is a considerable, the increase in data is not that to an extent, which is okay. And our observations after this here is data overhead is almost 27% increase when you use this HTTP, and at least for the model we produce, and also for write primitives, it is increasing almost 82%, which is actually a significant increase, which is a disadvantage of this approach, which we have to find certain, or we have to research in future how we can improve such situation. Perhaps when you create bulk request, you can consider certain data to be compressed, or that has to be really researched. So, and also the data type overhead created by this translation is negligible. So it is almost nil. And also the node ID translation procedure has a significant overhead. So this is something we have to consider. And okay, I'm coming to the future works. It is so that in future, so we have implemented and proven that this is possible using interoperability between OPC and HTTP. What we have observed here, or some parts to be improved here, is we only consider a subset of OPC modeling capabilities. So when you translate to another protocols, there is always this problem of losing some information. So how we can achieve an extensive modeling capability is something we have to research. And also the RTT overhead created by HTTP is also something we have to improve by a certain mechanism which we have to see in the future. And also a node ID translation can be improved by node ID caching in server. There's such thing improve average node ID translation delay, but not in worst case it is same. So that is something which is inevitable, but to a certain extent it can be avoided. But because we need to do some changes in server operations to do that. And in future works, we would like to extend this VAV architecture with other protocols like MQTT, TDS, and other IoT protocols, and also include security aspects of OPC UA in addition to public subscribe. So this is something we have to explore in the future. And thank you very much for listening to this presentation, and you are welcome to ask any questions if you have, or any points if you want to discuss.